All right. Hey, everybody. I'm just getting set up here. If you're catching the recording, skip to 5 or 6 minutes, and then we'll get started. We're just going to wait and see if anyone shows up here. I think the audio yesterday was a little weird, but I think I've got that figured out, so hopefully it's going to be better for us today. Awesome. I'll be right back. Yeah, just whenever I sign in on a personal account on a public computer. So that way it doesn't save all my passwords and stuff, so no one can be like, ooh, I'll log into this person's. Yeah. Okay. All right, hopefully this is working. How long have we been on for? It's 2:01. We'll just wait a couple minutes and see if anyone tries to join online. Otherwise, we'll give her. No, that's actually this computer that it thinks is Delaire. Yeah, it's just because the classes were all set up through her Zoom account because I don't have a paid version. So I can only do them for a certain amount of time before it cuts it off. Yeah, so Zoom will let you do, I think, 45-minute meetings as much as you want for free. But if you go ever over 45 minutes, yeah, that's what this is. So Zoom is what is recording me. And also if someone was joining online, they would be, yeah, it's like a conference call platform. So everyone has a webcam at their computer and everyone can sit at home and sort of see each other and interact and share their screen. So that's why when you watch the recording, you see what's on the whiteboard because this computer is sharing its screen. Yeah. Yeah, and then on the Facebook page, you can catch all the previous recordings from what we've been doing. So day 1 is a re-recorded version where it's just me in the room. Day 2, it's you and I. And day 3 will be the same. It'll be you and I again. I'm going to open up our calculator before we get going because we are definitely going to need that today. I'll take a look here with you in a sec. I want scientific and I want small and there. So today for the assessment page will be like covering question 5, 6. Yeah, question 5 and 6 basically is what today is going to specifically cover. And I'm hoping that I've got this calibrated better than I did yesterday. So let's start. For those of you joining us online, today we're talking about trigonometric functions. These are things for solving right triangles similar to Pythagoras. We can only do these things with right triangles, triangles with a right angle in one of the corners. The big annoyance and part of the reason, yes, I know I'm muted, go away. Part of the reason that yesterday I said the hardest time people have is labeling their triangle at the beginning is because we use a totally different labeling convention for this than we do for Pythagoras, which is really annoying. But that's okay, so we can learn that. Basically, we remember Pythagoras was always said what is directly across from the right angle, and Pythagoras would have said make that C. For these trig functions, we actually want to call this H, where H stands for hypotenuse. And a hypotenuse is just a big fancy word that means the longest side on a right triangle. So the side directly across from the right angle is always the longest side, and we call it the hypotenuse. Now, naming the other two sides with Pythagoras was arbitrary. We could just say they were A or B. Now we're actually going to switch our naming scheme from A and B to A and O. A for adjacent and O for opposite. Opposite and adjacent to what, right? So adjacent is like beside something. Opposite is like across from something. But we label our triangle as opposite and adjacent from an angle. So in this case, they've labeled an angle that we're going to use as our like point of interest in this equation. So opposite to that angle is always O, and beside it, the side that is not the hypotenuse that is touching this angle is always our adjacent side. That's our labeling for these trig function problems. The nice thing about trig functions is that they allow us to solve all the parts of a triangle. So Pythagoras lets us only solve for side lengths, which means we have sort of an arbitrary triangle. We don't know the internal angles. With this, as long as we have two side lengths or a side length and an angle, we can solve for every part of any triangle. So there are 3 trig functions, and each of them have a function in your calculator, so long as your calculator is a scientific calculator. In this case, because it's a digital calculator, I have a drop down. I can click on trigonometry and I have access to sine, cos, and tan. There are some other ones here, secant, cosecant, cotangent. We can ignore those. All we care about is sine, cos, and tan. Sometimes you'll hear tan as tangent. Tan is just a short form. And cos, sometimes you'll hear cosine, which is kind of confusing at times because it's sine is part of cosine. Cosine is cos, tangent is tan, and sine is always just sine. I don't know why it doesn't have a long form. I suppose sometimes people say sinusoidal, but that's kind of a different context. So we can remember how to use these functions with sort of a, I guess you call it a mnemonic device called SOHCAHTOA. So in SOHCAHTOA, I always write it kind of like this. Sometimes you'll see people just write it out like this. SOHCAHTOA. That works just fine too, but I find it easier to read in this form, and you'll see why in just a sec. In SOHCAHTOA, each of the big letters that are in front of sort of written as a fraction stands for one of our trig functions. So this says that sine of an angle, we denote angles with this symbol theta. It's arbitrary. We could have used x or y or whatever we wanted, but conventionally we use theta, is equal to a fraction of the opposite side length over the hypotenuse, where the hypotenuse is the longest side. Similarly, cos of an angle theta is equal to adjacent over the hypotenuse. Again, where the hypotenuse is the longest side, directly across in the right angle. And tan, or tangent, of an angle theta is equal to the opposite side length over the adjacent side length. So you can start to see here how, depending on what sides we have information about and what sides we want information about, we're going to have to use different functions. For example, if I wanted to know something about an adjacent side to some angle that I know, I definitely can't use sine, because sine has, in no place does sine mention the adjacent side. Okay, so we use this SOHCAHTOA kind of mnemonic device to figure out what trig function to use, but once we know which trig function to use, we use them all in the same way, which is the beautiful part of this. Ooh. So let's do an example and solve this triangle to find the side length of x. Some of us might look at this and want to do what we did yesterday. We might want to use Pythagoras. But what we'll realize quite quickly is that we're missing something. If we wanted to use Pythagoras to find x, we would have to have this side A and this side B both to solve for x, because x in Pythagoras' case would be c, right? And we're going to have too many variables we don't know. So we need to do something else. First step, just like Pythagoras, label the triangle. So what did we say? We said straight across from the right angle is always the hypotenuse. It's equal to h. Then we have an angle that we know. The angle that we know is going to be like our point of interest angle, okay? Across from the angle that we know, 23 degrees, is our opposite side. Another number that we know. And touching the angle we know, but not the hypotenuse, is our adjacent side. Okay, so now we have labeled adjacent, hypotenuse, and opposite sides of this triangle. We write out SOHCAHTOA. And we have to decide which trig function we can use. So we want the hypotenuse, and we have the opposite. So we need a trig function that uses the hypotenuse and the opposite, right? So, okay, we're using that one. And that means that sine of an angle theta is equal to opposite over hypotenuse. There's a bug in my face. Yeah, it's been hot, so they're all coming out. But so sine of an angle theta is opposite over hypotenuse. What's our angle theta? It's the point of interest, right? That angle that we labeled all of our numbers around. What is happening? Stop it. Right? So we can start to fill this in. This is sine of the angle we know. In this case is 23. Sine of 23 degrees, and that is equal to some fraction, opposite 2,500 meters, over x, the value we want. So now we have to solve this for x. You might have heard of something before, cross multiply and divide, right? Yeah, and you have two fractions. We can write sine 23 over 1. It's the same number, okay? When you have two fractions and there's one missing, you take the two numbers you have on an angle, in this case 2500, multiplied by the 1, and then we divide by the last number we have to get x, okay? So then that says that x is equal to 1 times 2500, which is just 2500, times sine, divide sine of 23. Now, if you're really clever and you know special angles, sometimes you can do trig functions in your head. We will never do that. We'll always use a calculator. It's much too difficult. So we go to our calculator, we say 2,500 meters, okay? We divide by a trigonometry function, sine. Nope, I've done this wrong. So this is pointing out differences in calculators. Technically, we've times it by 1, but what happens when you times something by 1? Stays the same, right? 1 times anything is itself. So I write this 1 here only so that I can say cross multiply and divide to help myself remember how I have to rearrange this, right? So alternatively, I could have gotten to the point where I had sine of 23 degrees equals 2,500 over x. And I could have said, okay, solve for x. Well, if I want to solve for x, I need x to be on the top of the equation, okay? So right now I'm dividing by x. Let's multiply by x and multiply by x. And then we're going to get x sine of 23 is equal to 2,500. And then we have to get this sine of 23 to the other side. Right now it's multiplying the x, so we have to divide the sine of 23, and we have to do it to both sides. Okay? Then my last step will say x is equal to 2,500 divide sine 23. Notice that's the same as 2,500 times 1 divide sine 23. Okay, so I write the over 1 so that way I can more easily understand myself when I say cross multiply and divide, and then I don't have to write out quite so much work to try to figure out how to actually simplify these problems. So back to the calculator. For these digital calculators, you have to type them in kind of a little bit weird. So we're going to go 2,500 divide. Oh, I've got stuff already in there from before. So I've cleared everything, 2,500, and then I hit divide, and I type in my angle first, and then I say this angle that I've typed in is actually in a trig function, and that function is sine. So 2,500 divided sine 23 is equal to 0.39. That's not what I want. What went wrong? Is this in radians? I bet you this is wanting me to use radians. So there are two modes in most calculators. Sometimes you talk about angles as degrees, and sometimes you talk about angles as radians. Radians are very useful to us when we start to do calculus and start to use calculus to find volumes and areas of shapes, but they're a whole sort of new ball game of learning to wrap your head around because everyone's traditionally used to angles. What I believe is happening right now is that this particular calculator wants me to be using radians. So what I'm going to do actually today, even though it's not going to be as good for those of you who are on the recording, I'm going to grab a physical calculator that I can change the mode 2 degrees. And I'll try to walk you through what I'm typing in as best as possible, just so we can get numbers. The difficult part, though, is done. At this point, we're just typing it into a calculator. So I'll be right back. Okay, so if I type this into a physical calculator that oh, this one's in radian mode too. Okay, this one's now in degree mode. Typically, if your calculator is in degree or radian mode, it'll say in little tiny letters right near the top of the screen. I'll show you that. You can see DEG right there. If you hit the mode button, which is that one, see how it changes? It says rad. And there's one more, gradients, which I've never actually found a use for. You want to make sure it's in degrees. If it's not in degrees, you get numbers that don't make any sense at all. Basically, the reason for that is that a whole circle in radians is 2 pi, so 6.28, where a whole circle in degrees is 360. Right, exactly. So radians are really useful when you when you start getting into calculus. They make a lot of problems a lot nicer. But when you're working and talking carpentry and sort of everyday problems, degrees are much friendlier because they're what we're used to thinking about, right? We all understand 360 degrees and 180 degrees and what those things mean. It's when you get even further complexity and you start dealing with multiple dimensions, basically. Okay, so I'm going to type this in real quick. So 2500, divide button, sine. Typically when you do a function, a trig function of any kind, you want to open brackets and put the degrees in them. So here we go. X is equal to 6,398. Does this make sense? Well, 2500 is on a vertical side, and we're looking for the hypotenuse. Hypotenuse must be the longest side of any triangle. So the fact this is bigger than that number bodes well for us. So this does make sense. That's why I realized right away, oh crap, that's in radians, because it gave me, I think, 0.9 or something like that. And I'm looking for a number bigger than 2500. Maybe it was 0.3. Either way, it started with 0, and I know it's supposed to be bigger than 2500, right? Because I know the side I'm looking for is the longest, okay? That's a really good trick when you're doing any trig problems, Pythagoras, trig functions, or otherwise. If you're looking for a side length and you know the hypotenuse or you do not know the hypotenuse, you have some idea of what range that number should be, right? If you know the hypotenuse, you know it's less than that. If you do not know the hypotenuse and you're looking for it, it has to be bigger than every side you already know. So once you get a number, that's a really good, like, super quick check. It doesn't tell you for sure that you're right, but it tells you at least that your answer makes some sense. So one more example, or a couple more examples. I can't remember exactly where this document goes from here. So let's find out. It'll be an adventure. So example 2. Again, we start by labeling our triangle. That's our right angle, straight across. Look, they've already labeled it for us. That's our hypotenuse, right? The angle we have is our point of interest. In this case, we have 34. Again, they've already labeled it for us. Across from 30 is the opposite. The side that is touching it is our adjacent side. So we're going to just solve this triangle. What I mean by solve the triangle is we're going to find every angle and every side length, okay? We're starting with just one side and one angle, and we know we can use SOHCAHTOA to start working through these problems. So I'm thinking ahead now because we're solving the whole triangle. And I'm thinking about Pythagoras and what side is easiest to find with Pythagoras. Pythagoras is always easiest to find the hypotenuse because it's on its own in the equation. It's the c squared part, okay? So if we're told to solve the triangle and we do not have the hypotenuse, the best thing we can do is find the opposite side or the adjacent side, the one we don't have first, and then use Pythagoras. I say this because I think Pythagoras is easier than trig functions. There's a little bit less room to make mistakes. So let's do that. We're gonna have the adjacent side and we're gonna find the opposite side first. We're gonna start there. So we have adjacent and opposite. We wanna use TOA, tan, okay? So tan of our angle, in this case, is 34. This is equal to the opposite side that we don't know over the adjacent side that we're told is 18 centimeters. Now, we want to rearrange this. We're going to put it over 1. We're going to cross multiply top number to bottom number, 18 times tan of 34. And then we divide by the last number that's left. In this case is 1. Dividing by 1 doesn't do anything though, right? Multiply any number by 1, it's itself. Divide any number by 1, also itself. So we can just ignore that and go 18 tan of 34. Again, I'm going to use a physical calculator because I can't figure out how to change the mode on that one. I'm hoping I will be able to for the next recording because that's going to be a lot better for those of you watching online. So I'm going to go 18 times tan, open a bracket, of 34. I'll show you what that looks like on my screen. Some calculators will make you put a multiplication sign in between the 18 and the 10. Sometimes they won't let you write it like this. It just depends on the brand. So if you ever type something like this in where you go 18 tan of 34 and it says error of any kind, it's probably because you don't have a multiplication symbol in the middle. Calculators are really annoying because there's no standard. So every calculator you buy does it all differently. So it's a big, big pain in the butt. But in any case, if I click enter on that, I'm going to get 12.14. So O equals 12.14 centimeters. There's a bunch more digits, but I'm just rounding to 2 because why not? Often if you're doing any kind of test or anything like that, they'll have a number of digits, but in real world problems, you'll have an idea how accurate you need to be and be able to make your own judgment of how far to round accordingly. Okay, so here we go. We've got 2 sides and 1 left to find. I mentioned earlier, I sort of preambled that it might be best for us to use Pythagoras to find the last side, so let's do that. We're gonna go Pythagoras. We gotta label it differently, so that's kind of annoying, right? Pythagoras goes across from the right angle and calls that c squared. And then he says, or sorry, he just calls that c, not c squared, but his formula is, oh, that's a big eraser. Forgot about that. In the red, that was the hypotenuse. In Pythagoras, this is c, and a and b don't matter. A, b. So Pythagoras says a squared plus b squared equals c squared. And we know a and b, so we can plug them in. That's 18 squared plus 12.14 squared equals c squared. We can type in the 18 squared plus 12.14 squared into our calculator. So 18 squared plus 12.14 squared equals 147.3738 actually, if we round that correctly. So I said 147.38 equals c squared. Square root both sides. The square and the square root cancel. We've got c is equal to whatever that number is. 147.37, hit the square root, is 12.14. And that doesn't make sense. Why doesn't that make sense? I say that doesn't make sense because we're looking for the hypotenuse. The hypotenuse should be the longest side, and we have a side that's 18. Okay, so I've done something wrong. I'm suspecting it is, again, an issue with me knowing how to use this particular calculator very well. So let's do it again. We're going to go 18 squared plus 12.14. So square of 18, I've hit the wrong button in there. So 18 squared button plus 12.14 squared button. Is that 147.3796? No. 147.3796, and we're going to square root that. Why do I keep getting 12.4? I'm going to type it in on this calculator and see if I get that number too, because that doesn't make sense. 18 squared plus 12.14 squared, square root the answer. 21.7 on this calculator. That makes sense. Why does this not like me? Okay, apparently I have to spend my time between these lessons figuring out the nitty-gritty details of this calculator, but it goes to my point a few minutes ago of how annoying calculators are. It does say degrees. Huh. Okay, well, I'm going to spend my time between these lessons figuring out that particular calculator a little more because I'm clearly just having problems typing incorrectly. We've got 21.7 when I type in the same thing on this calculator, which makes sense, right? Because we have a side that's 18. We're looking for the longest side, so we know it has to be longer than 18. So our last side equals, okay, what is all that? Go away, whatever it is. Wow, this really hates me today. I'm sorry, guys. Okay, got it. So 21.17, I think I said, is our last side. I've moved everything about, haven't I? So it all looks a little messy. But the last thing to do to solve a triangle is figure out the last angle. Okay? This is a lot easier than it seems like it's going to be. All you have to remember is that every triangle, the sum of all three angles inside is 180. No matter what the triangle looks like. So all we do is we take 100. Okay. All we do, y. My pens are broken. All we do is we take 180, the amount of degrees we know are the total inside the triangle, okay? And we subtract our 90-degree angle that we know and our 34-degree angle that we know. In that case, well, I can actually use this calculator because God knows I can't screw this one up. So 180, take away our 90 degrees that we know, and we take away again our 34 degrees that we know to give us 56. Okay, 56 degrees is our last angle. Oh, the pens are back. Ha! Just gotta wait sometimes, talk real pretty to them, and then they come back. 56 degrees, okay? So this has become a little bit of a mess, but we've solved the triangle, right? We know all three sides. We know 18 that was given, 12.14 centimeters we did with trig functions, 21.7 we did very badly with Pythagoras, but we got there. And then we have 56 degrees because we know the inside of a triangle is 180, and we moved on from there. Okay. So yeah, let's do one more. So this example kind of messes with us. It does that for one simple reason, and that's it put the triangle in a stupid position. Okay, so this is where labeling comes in important. Straight across from the right angle, this is our hypotenuse. Okay, straight across from the angle we know, that is our opposite. And the side touching the angle we know that is not the hypotenuse is our adjacent side. We are looking for something that uses the opposite and the hypotenuse because we know the hypotenuse and we want the opposite. So opposite hypotenuse. So sine of our angle theta is equal to the opposite over the hypotenuse. Okay? We plug into this equation with all the stuff we know. We know theta, sine of 57 degrees is equal to y, the number we want to find, over the hypotenuse, which is 15, given to us. And we rearrange this with cross multiply and divide, right? We know 15 times sine of 57. And we can divide by 1, but it doesn't do anything, right? So 15 sine of 57, I'm going to give it a shot. We're going to see what happens. We're on this rodeo together now. 15 times 57, and we want the trigonometry. We want the sine of that, which is equal to 12.58. Does that make sense? Our hypotenuse is 15. That's bigger and should be bigger than 12.58. So we can say that makes sense. I think I figured out the calculator. So what did I get again? 12.58. Okay, so that one's done. You can see if we're just looking for one side, once we get used to these trig functions, they really just go, right? They're confusing at first, and it's partially confusing because we're not used to having sort of these, like trig functions are kind of like this mysterious black box where we're like, oh, sine, yeah, it's a thing. And it's very difficult to understand what exactly sine is and how it comes to be mathematically until you get quite far into math. So it just sort of remains this weird black box, which is kind of frustrating. And a lot of times it's hard to be like, why does this work? It's very hard to kind of wrap your head around, and it takes some pretty advanced math, unfortunately. But suffice to say that they act sort of like operators, like multiplication, division. Yeah, and we can use them, and just like multiplication and division, they have what we call inverse functions, functions that undo them, okay? So you'll notice all of those examples we just did, we were looking for side lengths and not angles. But we can use trig functions to find angles if we only have side lengths. We do this by using what we call the inverse trig function, and we're gonna go over that in just a second. So an example of this, that's a pretty blurry example, but in any case, we still label our triangles just the same as when we're using trig functions with an angle, okay? So we go straight across from the right angle, and we say that that is the hypotenuse. And then we look here, see, this is the angle they want us to find. So we treat that as the sort of point of interest. Whatever angle we want to find, we go straight across from that. We call that the opposite, and the side touching that is not the hypotenuse is our adjacent side, okay? So we label these triangles exactly the same as we have been labeling them. It's just that we kind of have this weirdness where we don't know the angle that we're labeling. So now we have to figure out what to do. We know the opposite side, and we know the hypotenuse. The hypotenuse is 20, and the opposite side is 12. So again, we look at SOHCAHTOA. SOHCAHTOA, right? And we say we know opposite hypotenuse, that's sine. So we're gonna go sine of theta, that's the angle we're looking for and we don't know yet, is equal to the opposite side, 12, over the hypotenuse, 20. So this is all pretty straightforward. Now all we need to figure out how to do is get rid of sine. We have something I mentioned just a minute ago called the inverse trig function. And when we write inverse trig functions, they're exactly the same as the normal trig function with this -1 here. That -1 sort of stands for, in math, inverse, okay? So when you take the inverse of the entire side, you end up with an equation that looks like this. Okay, the entire function sine of theta is being acted on by this inverse. That's why we draw these square brackets here. And up here we have just theta in the brackets. So sine is only acting on theta, and sine inverse is acting on both of them as a whole. Because we took the inverse sine of the left-hand side, just like if we add or subtract something from an equation, we have to do the same thing to the right-hand side. Okay, so we're gonna go sine to the inverse of 12 over 20. And we get something that looks like this. Now this looks like a mess, right? It looks like something we have no idea how to deal with, but the really good thing about it is just like squares and square roots, sines and sine inverse cancel. So sine and sine inverse cancel each other, and they just drop theta out, okay? Again, this is one of those things that sucks because there's no good way to motivate it until we get to a much higher level of math, because you have to really understand where these functions come from. But when you take a sine inverse of sine, you get 1. And vice versa. If you take a sine of a sine inverse, it just goes away and whatever's inside it falls out, okay? So we have theta is equal to sine to the inverse of 12 over 20. And this is something we can type in a calculator. I'm going to be daring. We're going to type it in on this calculator, okay? Almost every calculator will have some sort of second function, alternate function, a button that says something like that. In this case, it says second. So see how I click that and it stays blue? That means every button in here will do its second function. In the case of trigonometry, when you've selected second, see it changes everything to inverse, right? That's the same on a physical calculator. What they do typically, this one uses orange, says second function is an orange button. All the orange letters above each button is what that will do if you select that when you have second enabled, right? So if I turn this on and hit second, you can actually see it right at the top. It tells you second is enabled. And then if I was to hit, say, sine, for example, it'll give me sine inverse, okay? So that's the same on this one. I hit second function and then I can go sine inverse. And I've forgotten again that this calculator, I'll have to type the number and then the function. So I'm going to do that now. I'm going to go open a bracket. I'm going to go 12 divide 20. I'm going to close a bracket and then I'm going to go trigonometry, second function, take the sine inverse of that, and that's 36.86 dot, 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 dot. So theta, our angle we're looking for, 36.86 degrees. Okay, so this is one of those, again, it's unfortunate, it's very, very difficult to motivate, but we treat it as kind of a black box. And we just have to remember that sine inverses cancel sines and vice versa, and it becomes relatively straightforward to simplify through these problems. How are we doing for time? 2:40, okay. Let's just do one of these two examples. Let's do this one. So we have, again, a function or triangle where we're looking for an angle. We do not know theta right here, so we're going to treat that as our sort of point of interest. We're going to go straight across from the right angle, and we're going to say this is equal to the hypotenuse. We're going to go straight across from theta, the point of interest, and say that is the opposite side. And then we're going to take the last side left and call it the adjacent side. So here we know two sides. We know the adjacent side and the hypotenuse. TOA, right? We know A and H. We want A and H. That's cos. We're going to go cos of theta is equal to A equals 15 over H equals 25. Okay, now what do? We want to find theta, so we have to get rid of cos. To get rid of cos, we use a cos inverse. So cos to the inverse of cos of theta is equal to cos to the inverse of 15 over 25, right? We just take cos inverse of both sides, and then we remember that cos inverse and cos cancel. To anyone watching the recording, sorry for the noise, deck still, so that's kind of annoying, but that's just how it goes. So theta is equal to this thing here, cos inverse of 15 over 25. Let's type it in on the calculator. Clear everything that's there, make sure for sure it's cleared. And then we go bracket, 15 divide 25, close the bracket, trigonometry, I want inverses of my trigonometry functions, and I want cos, equals 53.13, okay? Theta equals 53.13 degrees. So we start to see how that becomes very, very similar to trig functions. We label exactly the same. We select a function exactly the same. The only difference is instead of cross multiplying and dividing, you take an inverse trig function to get rid of the trig function and just be left with an angle, right? Other than that, they're exactly the same. So next, we're going to talk word problems. Again, the bane of everyone's existence, but the most practical use of math in my opinion. So it's good to talk about. So some guy named Steve wants to know how tall a pine tree in his backyard is. On a sunny day, he measures the tree's shadow to be 40 feet long, and at the same time, he measures the angle of the sun above the horizon to be 50 degrees. Okay, so he's got a pine tree. Let's start there. My amazing pine tree, okay? He does not know how tall this pine tree is. That's what we want to find out. At some point, he measures a shadow of this pine tree. And he says that that shadow was 40 meters long. Okay? What was making that shadow? Shadows are always made by the sun. We'll draw him up here. Happy little sun, like Bob Ross. You know Bob Ross? He's like, he does like videos of painting, and he's got a whole bunch of like weird anecdotal things. He always draws happy little suns and stuff like that. Anyways, so shadows, how are they made? They're made by light rays hitting the tree and going. So we can draw a line straight like this. This is the light ray that is the last light ray that's getting past the tree. Every other one down here is part of the shadow. Okay? We just take it as if light travels in a straight line. Unless it's hitting stuff, it does. Right? So we have a triangle here. We can pull that out of this picture because this picture is kind of messy and weird. Oh, actually, I'm not done. Why am I not done? He told us the shadow was 40 feet, not meters. Okay. Units are important. The shadow was 40 feet. I really wish this eraser was less big. And he also said that the sun above the horizon was 50 degrees. If this ground is flat, this ground is like the horizon, right? If the earth was flat, the horizon is just straight along the ground. If the sun's angle in the sky is 50 degrees above the horizon, then this angle is 50 degrees. Right? From the ground, if we call the ground the horizon, to where I see the sun, that angle that my arms make, even though this is really weird, is 50 degrees. Okay? So we can pull that triangle out. We know that there is a 90 degree where the tree meets the ground. We're assuming the tree is growing straight up and down. That's our 90 degree angle. And we have our hypotenuse right here because that's straight across, right? We know that this is equal to 50 degrees. That's the angle right here, pulled up into that triangle. And we know this side is 40 feet, not meters. We want to know this side, the height of the tree, right? So we have to label this. We go straight across from the angle we know. We call that the opposite. We take the hypotenuse across from the right angle, and the last side left is the adjacent side. We want the opposite side, and we have the adjacent side. So TOA has opposite and adjacent. So tan of the angle is equal to opposite over adjacent. We know the angle, theta is 50, so tan of 50 equals the opposite that we're trying to find, the height of the tree, over the adjacent, which we said was 40 feet. Right? Now, we can put this over 1, cross multiply and divide. Tan of 50 times 40 feet, divide by 1 is just tan 50 times 40 feet. Okay? I'm going to write 40 feet times tan 50 just because I think it looks nicer. Right? You can multiply any direction. 2 times 3 is the same as 3 times 2. I like to write my number I'm multiplying a trig function by before the trig function. And I do that because I could write this as 40 tan 50. I don't technically need the brackets. But if I wrote this so the 40 was on the other side, I definitely need the brackets, because then it looks like it's tan of 40 times 50, right? So that's just a preference, but I am going to try for our purposes to always write the brackets because it is not incorrect to have them even when you don't need them. And it's just a bit more rigorous. So that way, if your 40 is on the other side, it doesn't change the way the equation looks, okay? So we go open our calculator, clear everything that's in there, and we go 40 multiplied by 50 to the trigonometry function that is tan, and we say equals, and we get 47.67 ... right? And this was equal to x, so then x is equal to the 47.67 ... Does it make sense, right? What were we looking for? We were looking for opposite side, and we had an adjacent side, right? So we don't really know much in this case, right? Because we only had an adjacent side and we were looking for an opposite side, so we don't necessarily know if one has to be longer than the other, right? If we knew the hypotenuse, we could say, yes, one has to be longer than the other. But in this case, we don't know a lot. If you start to think about it more deeply, you can actually say that if this angle is bigger than 45, your opposite side should be bigger. And if the angle is less than 45, your opposite side should be smaller. And that's just because 45 is that halfway point between making a square, right? And if you think about it, if I make a triangle with a really extremely bigger than 45-degree angle, so I have like, right, and I want way bigger than 45 degrees, I'm gonna get something that looks like this, right? So this is really, really tall and really, really skinny. The opposite side is really, really tall. And as we go towards 45, it gets closer and closer to the same thing. At 45 is when they pass each other, and then it switches. So the adjacent side, the bottom side, will be longer and the triangle will be shorter. Okay, that's not something you have to know. That's just something that if you spend enough time with these, you'll start to recognize. So with that in hand, I can say 50 degrees is bigger than 45. So this side should be bigger than the horizontal side, which it was. 47.67 is bigger than 40. Everyone online, just like yesterday, I know we move pretty fast. This is a bit of a lot to cover in a week. So please, if you need to, pause and replay any segments. And also feel free to get a hold of me. I'm available through the Facebook group, or you can grab my email to ask me any questions you might have. So this is the last one for the day. This time it's Jenny. Jenny is setting up a ladder, and she needs the ladder to reach the top of a 10-meter tall building. She knows the ladder should be set up at an angle of 75 degrees for the safest use. So how far from the wall should Jenny place the bottom of the ladder? So what do we got? We've got a building, right? That's a building. I'd say so. That building is 10 meters tall, okay? And Jenny wants to place a ladder so that the ladder reaches the top of that building. Let's call that a ladder from the side view, right? Super good artist right here. And she knows that she needs that ladder to be set up at 75 degrees from the ground. We are going to make the same assumption we always do, that the ground is flat. Jenny is not on a hill because that would be difficult, and we don't like difficult. 75 degrees from the ground. Okay, so we start at the ground and we go till we hit the ladder. That's this angle. If it was 75 degrees from the wall, then it would be this angle. It is not that. I'm not going to erase that because my eraser is really big, so sorry, I guess, that, that there's a scribble there. But this one is the one we want, 75 degrees from the ground, right there. We know it is 10 meters tall, and that's all we know, but we want to know how far is the foot of the ladder from the wall. So again, we can pull that triangle out of this drawing. This one's not so messy, so we might not have to, but just for the sake of rigor, I'm going to. We have a vertical side that we said was 10 meters. We have a side on the bottom we don't know, and we have an angle here that is 75 degrees. We're assuming flat ground, and we're assuming the building was built straight, so that's 90 degrees. Okay, straight across from the 90 degrees is our hypotenuse. Straight across from the angle we know is our opposite side, and whatever's left is our adjacent side. So we know the opposite side, and we want the adjacent side. So we have to use our trig mantra, so katoa. Right, and we say opposite adjacent, toa, tan, right? Tan of what? Tan of the angle we know, which is 75 degrees, is equal to the opposite side, which is 10 meters, over the adjacent side, which we do not know. We'll just call it x, right? X is just a good, that's the thing we want variable. Right? So we're going to cross multiply and divide to solve this. We'll put tan of 75 over 1 because we're allowed to do that. We're going to go 10 multiplied by 1, divide the tan of 75. So 10 multiplied by 1 is just 10. We divide the tan of 75. And we set that equal to the number we're looking for, which is x. Right? Pull up a calculator, clear everything that's in there. We go 10 divide 75 degrees. We want a trigonometry function that is tan, and we have to hit equals 2.67 meters. 2.68 because it's 6, 7, 9. The 9's closer to 8, right? So 2.68 equals 2.68 meters. Does it make sense, right? We always ask ourselves this. If we look at my drawing, it doesn't seem like it makes sense. But this drawing is not to scale, right? This is definitely not 75 degrees. That's more like 15 or 20 degrees that I've drawn. I've just written that it's 75. So if we were to draw this actually at 75 degrees, I'm going to do it over here. We would have a horizontal side and a vertical side and something like that, right? 75 degrees is a big angle. It's close to 90. So this side should be a lot smaller than that side, right? 2.68 is a lot smaller than 10. That checks out as pretty accurate, right? At least it makes sense. We don't know if it's right, but we know it makes sense, and that's really important for us. Yeah, so that's all for today. That covers, what did I say it was? It was questions 5 and 6 of the assessment page that we handed out, and there will also be an associated worksheet with problems for this when we post the recording on Facebook. So thanks for watching, guys. I hope you found it useful.